Okay, yeah, please, Daniel, go ahead whenever you're ready.
Okay, nice to see everyone. So I guess I'll just keep going from where I was last time. And I'll start telling you how the how we can think about the Hull-Strominger system. So maybe I just remind you of the idea from last time. So I told you roughly there were two ways in which geometry appears in supergravity, and the two ways end up being connected if you think about it the right way. So one way was to take the example of four-dimensional theories with n=1 supersymmetry. That's four supercharges. And the idea is that the fields in the supergravity come in multiplets. And in particular, there are a set of fields which come in what are called chiral multiplets, which are necessarily complex scalars from the point of view of the four-dimensional theory. But they're not really scalars. They're really maps from the four-dimensional space into some Kähler-Hodge manifold. So that's a place where geometry appears, which is in the sort of space of scalar fields. And then if you, so this is the Lagrangian you get. So there's some Einstein curvature. This is some kinetic term for the scalar fields, which depends on the geometry. And there's a potential, and the potential depends on two things. One's called the superpotential, which is some holomorphic function of the on the Kähler space, and then there's also a moment map. And so you can think of looking for what are called supersymmetric Minkowski backgrounds, and two things happen. You get two types of condition. One is some F-term condition, what's called an F-term condition, which is to do with the superpotential, and that puts you on some complex submanifold in this Kähler space. And then you can do D-term conditions, which are basically Kähler quotients. So they're just a symplectic quotient for this moment map. Because everything's Kähler, you can also think of the symplectic quotient as instead a quotient by the complexification of the gauge group. So that's the sort of stability GIT picture. In fact, you can think of the Kähler potential on this space as playing the role of the norm functional for the stability. So you can also think of the zeros of the superpotential as the points that extremize the Kähler potential under the imaginary gauge transformations. So that was one way the geometry appeared. The other way the geometry appeared is like, let's look at 10 dimensions, and n=1 in 10 dimensions, which has 16 supercharges. There again, you have some multiplet of fields. One there's a gravity multiplet, the other is some vector multiplet. There's again some action, and this starts seeing things that you're used to from generalized geometry, where there's some curvature, some Dylaton function, and some three-form here, so three-form field strength, and some gauge fields, some curvatures for this these vector multiplets, which in general just are some connection. And you can look at a supersymmetric compactification, which means we assume the 10-dimensional space is some flat four-dimensional space plus some internal manifold, some six-dimensional internal manifold. And then you can ask, what is, if I want to have some preserved set of supersymmetries on this background? So that means some variation of the Fermi of the fields vanishes for some spinor. And that gives you a set of equations on the fields on the internal space. And in this particular case, they give you what are the equations of the Hull-Strominger system. So that's this set of equations. But the point was that you could, and that's some sort of generalization of Calabi-Yau. But the point was that you could equally well think about this in the four-dimensional language and think about the internal fields, the fields living on this space here, as being like an infinite set of these chiral multiplets I talked about before. So there ought to be somehow on this set of objects that are appearing here, I should be able to think of them as parameterizing some infinite dimensional Kähler space and think of these conditions as F terms and D terms. So that's what I tried to write here. So we should be able to think about these things as parameterizing some infinite dimensional Kähler space. And then those supersymmetry conditions should correspond to some moment map and some kind of extremizing some superpotential. So the question we're left with is how does that actually happen? And the reason I went through all that was to sort of convey to you that this is a very general thing. You can do this in lots and lots of different systems. You take your favorite 10 or 11 dimensional supergravity, you compactify on some 6, 7, 5, whatever dimensional space you want, and you look for a supersymmetric background, and it will always have some interpretation in terms of things like moment maps, simply because there's this way of thinking about it as though it was a lower dimensional theory with some infinite dimensional space of structures. So sorry, that was a bit quick, but I hope the general idea is there. Is that okay? Let me now try and go through for you in this particular case how that happens. So let's see. So I want to try and think about how each of these structures appear in the particular case of the whole Strominger system.
One quick question, Daniel, if I may.
Please, 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 please.
When you write these supersymmetric conditions in terms of the superpotential and stuff, you assume that the Gravitino equation has been solved, right? The Gravitino-Kleene-Spinor equation.
Yes, that's equivalent. So those conditions are equivalent to the Gravitino and Dylaton-Spinor conditions.
But what I mean is the Gravitino equation, which requires in this case that you have a spinor parallel under some spin C connection, perhaps coupled to other stuff, that needs to be resolved by separately, right?
Say it again, sorry. So I would say I have some Gravitino equation which says something like this is 0, and some Dylaton condition which says something, this has maybe got a half, this has maybe got a sixth.
Oh, but I meant in the for the n equals 1 supergravity, where you have also, I mean,
I understand. Sorry. So when right back here, when we look at the variation of the
exactly.
Yeah. So there's Gravitinos, there's Gauginos that come from the gauge multiplets, and there are fields that come from the chiral multiplets. And roughly speaking, the Gravitino equation says W is 0. The Gaugino equations say the moment map vanish, and the fermions that come with the chirals tell you that dW is 0.
But is this in a fixed background or something like that? Because the Gravitino equation requires that you have a spin C parallel spinor.
Yeah. Sorry, no, I understand. Yes. So we're looking specifically at Minkowski background. So it's flat.
Okay. Sorry. Okay. I see. Now everything makes sense. Sorry.
Sorry.
But it will hold more generally, perhaps, if you just assume if you just solve the Gravitino equation by itself, this parallelicity, then the same type of result will hold even beyond Minkowski space, right? Perhaps.
Yeah, you could. So, but what I wanted to do was specifically motivate exactly, so that you could make it more complicated like that. You could also look, I mean, the simplest way to make it more complicated would be look at, say, ADS, but yeah, you could absolutely do it more generally. Okay. But I wanted to treat the 4-dimensional space as kind of trivial and just focus on the internal space.
Okay, great, thanks.
Okay, sorry. Right, so I want to try and understand how the structures appear. And so they appear in through generalized geometry. So I want to talk about the notion of generalized structures. Because I think this is the easiest way to see what's going on. So let's, for simplicity, let's just ignore the gauge fields. So just to keep everything simple, I'm just going to think about the system which has the supergravity, doesn't have any gauge fields in the supergravity. You can add in the gauge fields, but just makes everything slightly more complicated. And I think for what you're interested for pluriclosed stuff, probably it's better to ignore them for now. So we want to do some generalized geometry. So we have some generalized tangent space, which we think of as just t plus t star. I'll write a generalized vector as having a vector plus a one form bit. And as you know, there's a natural metric on here, which I'll write as eta, which is, which is just the ODD metric. Just contracts the vectors in the one forms. And then we have a Dorfman derivative or Dorfman bracket, or some generalized Lie derivative. I tend to call it generalized Lie derivative, which has the usual form. So I'll sometimes write it in this LV, capital LV. It's the generalized Lie derivative. And as you know, this is just the ordinary Lie bracket, and then the Lie derivative, and then an extra term. So this is some exact current algebra. I could either think of adding a flux piece in here, or I can think of this as some twisted bundle and put the flux in the twisting, but those two things are equivalent. And then one can think about some generalized frame bundle. So let's call it F of E. So that's a frame bundle for E. And on there I have this is in general some SODD principal bundle. So now I just want to ever so slightly extend this. So we can extend this slightly. And let's call it E prime, which is just E, but together with some determinant factor of this, so some weight. And let's just assume everything's orientable for the moment. Then there's some corresponding frame bundle here. And on here, I can think of this as some SODD times R plus principal bundle, where the R plus is just doing this is just the rescaling the determinant factor. So I just want to promote things a little bit and just introduce this extra R plus scaling. If I do that, we can also extend the Dorfman bracket. So I can think of a generalized Lie derivative LV of V prime, which is just actually takes exactly the same form as before. Where now V is an ordinary generalized vector and V prime is one of these weighted things. And once I've done that, then I can think of a notion of a generalized tensor. And that's just some vector bundle for some representation of SODDR. And so, for example, if I can, there are two natural things, which are the spinor representations. And here I take them to be weight 0. Under the R plus. Or I could take them to serve some weight 1/2, and then this determinant factor goes, and these are just isomorphic to just odd or even forms. So it's the spinor rep with weight 1/2. So in one sense, the reason I introduced this weight is a way of actually defining something which is naturally just odd or even forms. It's also going to be the way we incorporate the dilaton. And then you can extend the action of LV to any generalized tensor. So you just by Leibniz. So the fact that the generalized Lie derivative preserves the ODD metric, this ODD metric means that we can extend it to any generalized tensor. Am I making sense? Yep. Okay. So now here's the notion of what we want to have.
Sorry.
So we can think of a general.
One question in this bracket that you have defined, which is only like so E prime is like a module for E. You don't need to choose anything, right? It's canonical. You don't need to choose a connection or anything.
No, this is this is canonical. Yep.
Okay.
Yep. Yeah, I basically extend onto the determinant factor just by taking the ordinary Lie derivative on any factor.
And sorry, can you go back to this the spinor thing? Like, isn't there some non-trivial power?
Yeah, thank you. Sorry, -1/2.
Okay, thank you.
Thank you. Thanks, Friedrich. Right. So then you can introduce what you might call a generalized G structure, just an analogy to the way you do it in ordinary geometry. So this is the same as just some, let me call it GS structure. This is just some GS principal subbundle. Oh. So some P inside this, this extended frame bundle. So GS is going to be some subgroup of SODD times R plus. So, and then typically this is going to be equivalent to some fixing some GS invariant generalized tensor. So you can think of these two different ways, either as choosing some subbundle or equivalently having some globally defined, nowhere vanishing GS invariant generalized tensor. So, for example, if we take GS to be SOD times SOD, this is equivalent to writing down some generalized metric. So this is sort of some like Riemann, this is the analog of Riemannian geometry. And the generalized metric, well, that has the usual form. So I call everything G, which is terrible, but that's some G, which looks like the usual form. Sorry. Which is some symmetric tensor in E star, but also because we have to fix the R plus action, it also determines something that, let's call it some volume form, which is e to the -2 phi times the square root of G. So by thinking about this as fixing some structure in this slightly larger group, we get both the ordinary generalized metric, which is encoding the metric and a B field, but you also get something which fixes where you are in the R plus direction, and that's encoding the dilaton. So this is some section of the determinant bundle. Now you can also define what you might call I'll call an integrable. An integrable GS structure. And that just corresponds to one that where there exists a torsion-free generalized, a torsion-free GS-compatible generalized connection. So you can define generalized connections in analogy to ordinary connections, and you can also define a notion of torsion. So, and just as in ordinary integrable G structures or torsion-free G structures, you can ask there to be able to find a connection which is torsion-free. And what happens here, so there's in general, there's a notion of generalized intrinsic torsion, which is just the obstruction to finding such a connection. So for example, in the case of the generalized Riemannian geometry, when you're doing this, just as in ordinary geometry, there's no obstruction to finding such a connection. So you can always define the analog of a Levi-Civita connection. But in other cases, there may be some obstruction. And I should say here, in general, the torsion in this case is going to be some element of wedge 3 of E plus E. And this extra factor, often the torsion is just written as something in here. This extra factor here is becoming precisely because we've included this R plus direction. It's R plus scaling. So sometimes when people construct the generalized Ricci tensor, you have to choose some torsion-free connection, but you also have to choose some kind of divergence or something. In this language, that just comes from setting this part of the torsion to 0. So it's not an additional thing you have to choose, it's just sort of part of the way the generalized connection is torsion-free. And then we have some other examples. So for D equals 2n, this covers the things you're used to. So a generalized complex structure would just be some integrable UNN times R plus structure. And if I had some generalized Calabi-Yau structure, that would be some integrable SUNN structure. So again, there's some invariant tensors. So you can think of this one as defined by some J, which is some endomorphism of E, or here you can think of it as some generalized spinor, which is some section of plus or minus 1/2. So this is some pure spinor. Or equivalently here, you could also think of it as the, as you know, as the decomposition of E into L plus L bar. And you can keep going. So things like generalized Kähler would be some UN times R plus structure, etc. And in each case, the integrability gives you, so the existence of this torsion-free connection gives you exactly the integrability you're used to. So torsion-free for this condition tells you that this bundle is involutive. Here it tells you the spinor is closed and so on. Okay.
Can I add something?
Yep.
Yeah. This bundle E prime, does it have a pairing or?
So it just has a pairing into so it just would have a pairing that took S2 E prime into the determinant. Just that, you just use the same pairing that you have on the other one, but it doesn't pair to functions.
Yeah, then I'm a bit confused. How do you define torsion? Because I mean, without the twisting, you use the the pairing to?
So I define torsion by saying that if I take the generalized Lie derivative calculated with the connection, I'll tell you what I mean, minus the ordinary generalized derivative acting on any tensor, this is some torsion acting on the tensor. So you know that in coordinates, I can write the generalized Lie derivative as something like this, where here I project onto the adjoint bundle. So I don't know if that let me just tell you what I mean by I have to tell you what I mean by this object. I hope this is going to answer your question, but let's see. By this, what I mean is I take the derivative. I take the derivative along V. Sorry. I take the generalized derivative along V, and then I subtract from that, where this is some projection onto the adjoint bundle of this f of E prime. So this is something that looks like the Lie algebra together with R. So I have to tell you exactly how I project onto R, but there's a definite projection. And then the difference between this object calculated, so this object, which depends on the connection, and the ordinary derivative acting on any tensor, that will give me a tensor. And that gives me some tensor T of V. And I think of T as being a map from E into the adjoint bundle. Or equivalently, I can think of T as being element of a section of the adjoint bundle times E star. And it turns out that what actually appears in here is just wedge 3 E star plus E star. Did that help, Mario, or did I miss your question completely?
Yeah. I still have to think about it, but yeah, it is.
Okay.
Thanks.
So this is like, you can do the same thing with ordinary Lie derivatives. You can always take the difference between the Lie derivative calculated with some connection and the ordinary Lie derivative acting on some tensor. And that will always be the torsion acting on that tensor, acting by just the ordinary endomorphisms. So it's just borrowing that definition and just doing the analogous thing. So there's actually a very kind of general result. So I'm not really telling you under what circumstances, but essentially there's a general result that a supersymmetric Minkowski background is equivalent to a integrable generalized G structure. So on here, I mean some Minkowski space in P dimensions times some internal space. So if I'm focusing on the geometry on this internal space, and I'm compactifying 10 or 11 dimensions, that geometry is always described by some integrable generalized G structure. Okay, so what I have to do now is I have to tell you what structure appears for the, so I have to tell you what the structure is for the Hull-Strominger system. So it turns out we want an SU3 times SO6 structure inside SO66 times R plus. So I can define that. So actually it's useful to think of two slightly different things. So there's one case where I take the structure to be SU3 times SO6. And then I can think of that actually as defined, the invariant tensor is some object which is a section of wedge 3 of E complexified, tensor a determinant bundle. Or I can think of a slightly weaker structure, which I'll think of as U3 times SO6 times R plus. And that's defined again by some kind of endomorphism. And this second case is equivalent to saying that the complexification of the generalized tangent space decomposes into 3 bits, where this is the plus I eigenstate, the minus I eigenstate, and this has 0 eigenvalue. So this space will be 3-dimensional, this will be 3-dimensional, and this is 6-dimensional. So in the supergravity, I can only really do this when I compactify on a 6-dimensional space. So instead of, I've gone from general D to 6 dimensions now. But I think you can extend this to any dimension in a straightforward way. But this is the one that naturally appears in supergravity. So this structure is a bit like a generalized complex structure, but it's instead of having just plus and minus eigenvalues, it's now got 3 eigenvalues, plus I, minus I, and 0. So you can ask, one can write general elements here. So equivalently, so generically, so you can similarly define this structure by how you pick out this space, or equivalently this space. So generically, you find that this L-1 can be written in the following way. It's some E to the B minus IW times some T10. So you find that this has some, so this is equivalent to specifying some Kähler structure, some U3 structure. So that's some complex structure and some symplectic structure together with a B field. Or if you're interested in this object, then you can write it generally as some twist, sorry, that's the minus sign, some E to the minus 2 phi, E to the minus B minus I omega of some omega, where, so this is some SU3 structure with a B field and a dilaton. And I'm thinking here of this wedge 3E tensor, the determinant bundle. This has a leading bit which looks like wedge 3 T star. The next bit looks like wedge 4 T star times T star plus wedge 5 T star times wedge 2 T star plus wedge 6 T star times wedge 3 T star. And this this holomorphic 3 form is just living here. So these actions are just the adjoint action in ODD. So in general, when I add here, it will grow up pieces here. So you can see what I told you, what I claimed, which is that the data of the whole Strominger system, which were this some SU3 structure, some B field, and some dilaton, is actually just equivalent to this structure psi. Is that okay? Yep.
Yes.
Please interrupt if I'm not making sense. So Now the point is, what about, so for the space of structures, so let's call it Z, you can think of, if you like, you can think of psi as a map from the space of structures into these this space of sections. And this is a holomorphic map. So this defines, if you like, the complex structure on here. And then this actually has or equivalently, if you like, you can think about the space of structures as being a space of sections of some bundle Q, where Q is a fibration of a particular coset space over the manifold. So this is just saying point by point, I need to choose an element of this space in order to define the structure. And this space here, this space C, so C has a natural Kähler cone structure on it. It's just inherited from the fact that it's appearing as this coset. So from that, you get a Kähler geometry on Z that's inherited point by point over the manifold. So in particular, I can write down a Kähler potential. Let's call it K on Z, which is just.
Sorry, can you say again what is Q? Q is what?
What Q is?
Yeah.
So Q is a fibration over the manifold where the fibers are coset spaces. So the fibers are these coset spaces. So.
Yeah, no, I got, okay, this is the fiber.
Sorry, yeah. And then the point is the coset space have a natural metric on them, and that sort of then gives you a metric on this space of sections.
Yeah. And in the previous slide, when you say that that there is this holomorphic map from Z to, so how does this work? So
I'm thinking of each structure. I can think of points in the space of structures as a choice of psi, in the same way that a choice of SL3C structure would be a choice of holomorphic 3 form, right?
Yeah.
So, but this psi naturally lives in this space of sections, and there's a natural complex structure on there that's just from the complexifications, just as a vector space, that space of sections. And the point is that this is a holomorphic, so I can think of this as taking, for each structure, I get some psi. So I can think of it as a map from points in Z into sections of this. This has a complex structure on it, and this map is holomorphic. So that effectively defines the complex structure on there. So I'm just trying to tell you what the complex structure is on here.
Can one describe what conditions there are on psi such that it corresponds to this quadruple of data?
Yeah, you can. It's easier to describe it on this guy. And then that defines a line bundle, and psi is just a section of that line bundle. Mm-hmm. So I would have to remind myself.
No, I'm just wondering if it's possible or.
You can.
Okay,
So there's
okay,
a set of algebraic conditions that this has to satisfy in order to define the right structure.
Right.
And the
Thank you.
general solution of those conditions is this form.
Mm-hmm. Thank you.
So that was the complex structure. For the symplectic structure, rather than give you the symplectic form, I'm just going to tell you what the Kähler potential is because it's globally defined actually on this space. And it's given by this, an integral over the manifold of, and then I'm going to take eta of psi bar to the half power. So I'm just gonna, this is just the SO66 norm, right? So remember, psi was some section of wedge 3e tensor this determinant bundle. So I can use the metric to take a norm on this part. So I'll get something in the determinant bundle squared. I then take the square root of that and integrate it over the manifold. And if you work out what this is for this particular case, this is none other than just the integral of I e to the minus 2 phi omega wedge omega bar. So by taking derivatives of the Kähler potential in the usual way, that defines the symplectic form. So really all I want to get across is that there's a natural Kähler metric on here. And once you know that, you know everything. That just gives you a Kähler metric on this space. Now, I should say there's also a natural Kähler metric on the space of J's. So the, in other words, the U3 times SO6 times us plus structure. And that's just inherited from the fact that this thing is a cone over another Kähler metric, and that's the Kähler metric on the coset associated to this. So actually you get a natural Kähler metric both on the space of these structures, both on the space of these structures, and also on the space of these structures, which is equivalent to this choice. Okay, so what about the supersymmetry? So for supersymmetry, this should be equivalent to a torsion-free structure. And this, from the motivation we had before, we should be able to describe it in terms of F terms and D terms. So let's start with the F terms. So the F terms turn out to correspond to, you can think of them as a superpotential, but I'm not going to do it that way. It turns out that they correspond to some involutivity condition. So they say that if you take the generalized derivative between two, or the Dorfman bracket between two objects, this is an element, let me write it with a Dorfman bracket. It's the same thing, but if you take the Dorfman bracket between two things, this is a section of L-1 for all V and W that are sections of L-1. So it's just like ordinary complex structures or generalized complex structures, you get some involutive condition. And it turns out that's the same as saying you have an integrable U3 times SO6 times R plus structure. So just requiring the integrability of the weaker structure, the integrability of the weaker structure is just this involutive condition. And what does it correspond to? It tells you that it's also equivalent in terms of the things that build up this structure. So this structure was made out of some ordinary complex structure or almost complex structure, some almost symplectic structure and a B field. And the conditions that this involutivity tell you are just that I is integrable. So we have an honest complex structure. And it tells you that H plus IDW, if you look at the 2,1 and the 0,3 components, these have to vanish. Or equivalently that DC of W looks something like H. So I think these are the same as the pluriclosed conditions. Is that right?
Yeah, that's right. Yeah.
Yeah. So that's part of what goes on. And then one needs to look at the D terms. And they should come from some moment map. And what is the moment map? So what's the group? So the group for the moment map is just the generalized diffeomorphisms, which is basically diffeomorphisms plus gauge transformations. So that I just mean the change in the B field is d lambda. So let's call this G diff. So the Lie algebra is just generated by the Dorfman bracket. So it's just generated by generalized Lie derivatives. So where V is psi plus lambda. So these are the diffeos and these are the gauge transformations. And what's the moment map? Well, we have a symplectic form. You can work it through. You find that the moment map is given by the following expression. So -1/2 I, some integral over the manifold. Again, we can take some pairing. And then we just get eta LV of psi bar. And so again, these things here are just using the ODD metric to pair things up.
Are these two things summing up, or?
Sorry, say again.
Is this a product or what?
So this is, yes, so times. So this is this will be, sorry, this object will be something that transforms like inverse powers the determinant bundle. This object transforms like the determinant bundle squared. So the whole thing transforms like the determinant bundle. So I can integrate it over the manifold. Yeah, maybe might be better to write it as a, this divided by this thing. If you allow me to raise, maybe I should write it as just this divided by. And if you work out what this is, you find that it's given by the following thing.
Before you wrote down the Keller potential as the integral of eta psi bar, right?
To the half. Yeah. So if I take sine psi bar and eta with it, that's naturally something that transforms in the determinant bundle squared. So the whole thing here, I get a determinant bundle squared from the top, determinant bundle from the bottom. So this thing is like a determinant bundle, so I can integrate it.
Okay.
And if you work it out, you get the following. So if we're on the if we have an involutive structure, so if I'm already satisfying these conditions, that tells me that I can write the exterior derivative of the holomorphic 3 form will be some one form wedge the holomorphic 3 form. It can only have a 3-1 component. The other components vanish because the complex structure is integrable. And then what happens is that this thing becomes some integral of IV, and then you have some 2 derivative of phi minus 2 del bar of phi minus A plus A bar times omega wedge omega bar. And then you get another term, which is 2 lambda wedge d eta minus 2 phi omega wedge omega. So setting the moment map.
What is A? What is A?
So A is the thing that appears, if I have an involutive structure, I have a complex structure. That means that the exterior derivative of the holomorphic 3 form is not closed, but it's a some one form wedge omega. And let's call that one form little a. Or here the A bar. It's like the Kähler connection. So I'm assuming that I'm already on an involutive structure. So you see that the moment map condition gives you these other, so mu equals 0 corresponds to setting d e to the minus 2 phi omega wedge omega is 0. So this is some kind of conformally balanced. And effectively,
Can you go one moment to the previous slide just to see the last term?
of course, yeah, sorry.
And the lambda is the variation of.
Yeah, so sorry, I messed up my notation. Let's write this as psi. That's better. Oh. Yeah, so I'm doing the variation. I'm choosing the algebra element to be psi plus lambda.
Okay.
So effective, yeah. So the generalized, the G-Diffley algebra is parameterized by generalized vectors. And the value of the moment map on that generalized vector is given by this. So I need to set this to 0 for all psi and lambda. And so that sets this factor to 0. And then effectively it sets A equal to d phi. So I can think of that as setting this equation. So these are the remaining remaining equations. The whole Strominger system. So we sort of have this picture that we start with this space Z, which is Kähler. And then in here, we embed the space Z hat, which is the F terms, or equivalently, this is the involutive structures, or equivalently the pluriclosed. And then from here, we can take a quotient to some moduli space, which should sort of be this. So it should be something like points in here, such that the moment map vanishes, and then we mod out by generalized diffeomorphisms.
So that last arrow is not really an arrow, right? I mean, it's not a map. It's just like a procedure.
Yeah, sorry. Yeah. So we satisfy the vanishing of the F terms and the moment map up to our symmetries, which are exactly the generalized diffeomorphisms. Now, in this case, the supersymmetry conditions imply the supergravity equations of motion. These are elliptic, so you'd expect this to be, so M should be finite dimensional. But actually in this case, if I turn off the gauge fields, there's also a no-go theorem. Which says that we must have H equals 0 and the geometry is just Calabi-Yau. So in that case, actually this procedure must put us actually just on Calabi-Yau geometries.
Sorry, you said that this is in the case you have the gauge fields, or
if you don't have any gauge fields.
If you don't have, okay, sorry.
Yeah. Now there's a couple of things to say about what's going on here. So, okay, so let me say one other thing.
Just one moment. So the symmetries, you only take the symmetries of E. So E prime does not involve, E prime is not involved in the
no,
symmetry.
so the parameters of the diffeomorphisms live in E. So the generalized Lie derivative is always with respect to some element of E, not an element of E prime. But you can take the generalized derivative of elements of E prime. Yeah. Yeah. Okay. So let me say one other thing. So the GIT picture, so we should also be able to sort of think of this moduli space as being some Z hat quotiented by the complexified gauge group. That would say that setting mu equals to 0 should be equivalent to extremizing this scalar potential, which was this integral of eta z over this complexified gauge group. So the now really complexifying the gauge group is complicated because it's diffeomorphism, but maybe it's better to think about complexifying the Lie algebra. So you probably really want to hear complexify the action of GDiff. So that's got some action by vectors, and there's a complex structure, so you can just multiply by the complex structure.
Sorry, when I read your formula for the moment map, it's not clear to me that this K is the norm squared of the moment map. Is it?
So if you have a cone geometry and a moment map that preserves the cone direction, then and it preserves the Kähler structure, then it's always true that setting the moment map to 0 is the same as extremizing the Kähler potential.
Yeah,
So
before you mentioned that the Kähler potential is something like the norm square of the moment map or something.
No, it's the norm functional, which is not the same as the norm squared as the moment map. Sorry, yeah. So in the GIT picture, you think about some function that lives in, let's see if I can get this right. So you have some space. I should probably call it something else. Let's call it Y. And then over Y, you've got some line bundle that's telling you, and this space Y is some Kähler Hodge manifold. And then there's some norm functional, which is a section of this line bundle. So, and that's the thing which is extremized when you hit the moment, when you hit the zero of the moment map. So this space Z is actually the space of this line bundle. So I'm actually working on this line bundle, and over that line bundle, there's a natural Kähler metric. It's a cone over this space. And in that case, the Kähler potential on this space is just the norm function. I'm not sure that helps at all. I mean, this usual kind of picture where these are the fibers of L, you have some function on them, and it has some minimum, and that minimum is just where the moment map is zero. And you just do some standard thing. You just use the complex structure and the fact that the moment map, the fact that I'm not sure I can reproduce it, but the fact that this is for some vector into the symplectic form, you just use that, and you use the complex structure and the fact that the symplectic form looks like dc of the Kähler potential. And just using that information, you can show that setting the moment map to zero is the same as extremizing this. It's roughly, you know, you pull one derivative of, sorry, to remember how this works, but you pull one derivative off here to set mu to zero. That's like pulling one derivative off here, which is like setting, so that's like setting derivatives of K to zero. Right, but something slightly weird is going on here, because if you look at the expression for the moment map, there are different V's which give you the same moment map. So any two Xi's which have the same inner product with this one form, so this just contracts the vector into this one form. Any two Xi's which have the same contraction will give the same moment map. But that's bad, something's going wrong, because it should be that I get a different value of the moment map for each element of the Lie algebra. Not only that, but if you think about this space, if this metric on here was a good Kähler metric, if I take any holomorphic submanifold, I should get a Kähler metric on the submanifold. But it turns out actually the metric on here is not Kähler, but it's like indefinite. It's got an indefinite metric. And so it's got positive and negative directions in it. And when you have an indefinite metric, when you take a holomorphic slice, it's no longer true that that slice has to be Kähler. So let me give you a really simple example. So suppose I just have I dz1 wedge dz1 bar minus I dz2 wedge dz2 bar. So that's some Kähler form that has an indefinite metric with respect to the complex structure. And I just set Z1 equal to Z2, that's some holomorphic slice. Well, then omega restricted to Z1 equals Z2 is just zero. So when you restrict the Kähler structure on here to this slice, it can actually give you a degenerate symplectic structure. And that's exactly what's happening. But it happens in a very controlled way, which is some of these, so you get a degenerate structure there, and furthermore, on the moment map, not all elements of the group action are giving different moment maps. So there's some degeneracy. But what happens is precisely the degenerate things in the moment map act on this space and take it from a degenerate symplectic Kähler manifold to an honest Kähler manifold. They get rid of the degenerate directions, and then you're just left with some moment map for whatever's left over. So I don't know how to split that. I don't know how to split the group sensibly, but effectively, so it's still true that this moduli space, where you take this holomorphic condition, set the moment map to 0, and then mod out by everything, gives you a nice sensible moduli space. But the modding out here does two different things. Part of it takes the symplectic quotient in the sensible way on here, but another part of it acts on this space, which a priori had a degenerate symplectic form on it, and makes it into a space with an honest symplectic form. So another way of saying it would be, if you did the moment map first and then took the holomorphic slice, then I think everything would be okay. But if you want to think of taking the holomorphic slice and then taking the moment map, it gets more complicated. So that's not discussed in the paper, but I just thinking about it for giving this talk, I realized that it always bothered me that we have this degeneracy that different size can give you the same moment map, and I think that's what's going on.
Well, is there a finite dimensional example which clarifies this picture? So you are saying essentially that the moment map, I mean, there are directions in the Lie algebra, says that the moment map remains fixed when I move that thing, right?
Yeah, so you can take exactly examples like this and do translations in the Z1 and Z2. So if I took an action, which was, I'll probably get it wrong, but if I took an action here, so I just took some action where I act by a vector, which looks like I Z1 D1 minus Z1 bar D1 bar plus I Z2. So sorry.
I think you can also say that if you have a group which acts trivially, then you can always take the trivial moment map, and that one will have that property.
Yeah, but let me give you something more interesting.
So, but I mean, from this thing, you see that, like, I mean, I don't know if that's the general rule, but like if this happens, it seems that there is like an part of the group which doesn't really act.
Yeah, it's not that's going on. It's specifically because you have this indefinite metric. So,
Okay.
Well, it is a bit like that, but it comes in two steps. So I could take this action where I just do phase rotations on each Z. That's a perfectly good moment map on here. So for the symplectic form, it's a perfectly good moment map. But if I was to take this slice, then I no longer have a symplectic form on here. And on this slice, this action, there's no symplectic form, and this action and its complexification are related to each other. So I probably need another. That's not a very convincing argument for you, Mario. But you can certainly come up with examples by just doing simple U1 rotations on flat space. But it's this combination.
What you were saying that you have a singular moment map, so you will get a singular. It's even worse than that, right? Because you have a singular moment map. You even have a maybe they generate symplectic structure.
Yeah, so the moment map on this original space Z is perfectly well defined. It's got no singularities. Everything's fine. The problem is if I want to think about it as acting on this holomorphic slice.
Yeah, when I say
Sorry.
singular, I mean that the differential of the moment is very degenerate. It's smooth, but has very degenerate.
Mm-hmm. So I think, yeah, so there's something to get to the bottom of exactly what's happening. But I think the final space should be perfectly well defined. So that's one direction. The other direction is to try and get away from this condition that we're just stuck in Calabi-Yau, and maybe get closer to the kind of flows that you guys are interested in. So so what about just U3 times SO6 times R plus structures? So I told you there that the integrability just corresponded to the involutivity, which was the same as the pluriclosed. So this is sort of the analog of Kähler, right? In the same sense that, so when I went to these, when I made this SU3, that was like the analog of going to, that was like the analog of Calabi-Yau. So if I'm dropping this, this is like the analog of Kähler. And then we want some extra condition, which I guess is sort of the analog of Kähler-Einstein or something, but at least gives you some set of special metrics somehow. And that should be playing, so in a sense, this Calabi-Yau case is sort of some special case of that. And these extra conditions came from moment maps. So it's like we'd still want to have a moment map on this space. But I think you can do that. So you can take this action of the generalized Lie derivative, and it will still act actually on this space of these structures. So there is some other moduli space here. I don't know what to call it. There is some other space here. Let's call it Y again, which is this space of U3 times SO6 times R plus structures. And you can actually get that from a symplectic quotient of the Z, where you take the action where you just multiply this by a phase, a local phase. But to make sense of this space, you need to choose some kind of volume form. Because we needed the Kähler metric to look like some integral of something over the manifold. In this case, you had a natural thing to integrate, which was based on this. Here, you don't get any volume form for free, so you have to choose a volume form. The same thing is when you take this symplectic quotient, you don't set the moment map to 0, you set it equal to something, and the thing you set it equal to is a volume form. So there is a natural space of, there is a natural Kähler metric on this space of structures, but it requires a little bit more information, which is a volume form. There is a natural candidate. So there's some volume form you need to choose here. So I'm just rambling now. There's some natural candidate, which is that you just choose the square root of G. So the only thing I think I really want to say is that on here, there was a natural action of generalized diffeomorphisms, that actually also becomes a natural action of generalized diffeomorphisms on here, maybe up to things that preserve a volume form. I'm not quite sure, but you can certainly, but there will be some action. So there will be some moment map. There will be some moment map mu on Y, which is inherited from the moment map on Z. And there will similarly, you will be able to reinterpret that moment map as the extremization of some Kähler potential. So I think that's really all I want to say, but there should be some way of going from the moment maps I've written down on this space to moment maps on this space. I've probably rambled on for long enough.
Okay, yeah,
please
thanks. Thanks, Daniel.
Please ask me more questions.
More questions?
I have a quick question, if I may.
Yeah.
So I understand that this mechanism, this technology allows you to compute, or a priori, the scalar manifold of the corresponding effective four-dimensional theory, and it was one, right?
Yep.
I was wondering about if the same technology can be used to compute the period matrix of or the positive complex polarization that determines the gauge sector of the theory, because that would be amazing. So.
Are you thinking of N equal 2 theories, really?
No, actually, I'm thinking about N equals 1 theories, and this brings me also to perhaps another question related to your exposition of N equals 1 supergravity, which I missed live, but I saw on YouTube. So that was very convenient that all these lectures are on YouTube. So there, if I'm not mistaken, you were describing gauge N equals 1 supergravity with no abelian gauge sector,
with no gauge kinetic function, you mean?
What I mean is that certainly it was gauge supergravity, right?
Yep.
Okay, because for the gauge sector of the theory, I would have expected a gauge sector that depends on the choice of period matrix, right? An abelian gauge sector, which I didn't see. I thought you simply were not. I mean, didn't have time to.
I ignored that.
Yeah.
Sorry, I understand your question. Yeah, I haven't thought. I honestly haven't thought about that, Carlos. I think
because it would be From your picture, one should expect that there exists a flat symplectic vector bundle over this infinite dimensional manifold equipped with a positive complex polarization that upon reduction gives you the desired gauge sector. And I was curious if you had thought about this, because that would be some sort of universal bundle that determines the gauge sector upon reduction.
Yeah, so I think the existence of the symplectic bundles, flat symplectic bundles, sounds pretty plausible to me. But the polarization is more complicated, I agree. So I'd have to think about it, but that's a really good point.
Well, so currently there are no results available in this direction, right?
Yeah. No,
okay.
That's good. That's good.
Okay, thanks.
I have one question. In this last picture that you're talking about, this U3 cross SO6 case, the group is still the same. So just by naive guess, you will get an equation for which involves a 5 form. And I guess the other one will be the same. My point is that I don't see, I mean, the nice thing will be to have a moment map picture for the Bismuth-Ricci form equals to 0. But this is a Bismuth-Ricci form, But this is,
So, yes, I have one very, very vague thought about that, which is that if you go back to, all the equations I'm getting are first order, and you want second order equations, right?
Yeah.
You want some Ricci tensor, right? Yeah. So all I would say is like, somehow what one really wants in this picture is the subset of the generalized diffeomorphisms, which actually appear non-trivially in here, right? By taking all diffeomorphisms, we're getting too many things because some of them are degenerate. Now, if you imagine complexifying this group, if you ask how it acts on psi, the complexified action is equivalent to the diffeomorphisms, the complexified diffeomorphisms, or let me complexify the generalized diffeomorphisms. They act just by ordinary diffeomorphisms, plus a little bit more, and the little bit more is the complexification of the gauge transformations. And then when you complexify this bit, all it does is rescale psi. So in some sense, the group that's left over here is something that just rescales psi and something which, and then transformations for lambda. So that rescaling of psi is very like the way you solve the Monge-Ampère equation, right? So that's a rescaling between the normalization defined using the holomorphic 3 form and the one defined using omega. So put another way, the feeling is that the subgroup that acts here meaningfully is far from the whole diffeomorphisms. It's something much smaller. And in the case of here, where you take h to 0, you sort of want it to be symplectomorphisms. If it was just symplectomorphisms, then this moment map becomes nothing other than the curvature moment map. So if I write in here, if I assume that this psi is actually a symplectomorphism, and I turn off the gauge field, I turn off set h to 0, then this moment map becomes just the curvature.
Do you mean the scalar curvature? Is that
The scalar curvature, yeah.
Okay.
So,
but I guess for that you're assuming somehow that you have no torsion, right?
yeah. So, but in some sense, I think, so very vague, but if somehow the actual part of the group that acts non-degenerately on here is actually something like symplectomorphisms, then you've got something where you could get back and get a second order equation. So I don't know what to say, but that's the feel of it.
And I had another question. So when you have gauge fields into this picture, and as you said here, for when there is no gauge fields, there is this no-go theorem.
Yep.
So if I have gauge fields, I have also to allow this nabla connection to be there.
Yep.
Let's suppose that depends on the rest of parameters. But then when you do that, the way you solve the Bianchi identity is the difference of signs between the trace of R squared minus trace of F squared. This also brings some indefinite directions in the metric on the moduli space.
Yeah.
So I wonder if there is, I mean, let's assume that you can do some perturbative analysis and say that nabla is nabla minus.
Yep.
And so does this solve the problem? Does this give you a Keller metric?
Does this solve, does the...
Yeah, so say that you cook up a metric on the moduli space with gauge fields. And I take the natural one, which I mean, at least from what we got in our calculations, the natural one on the bundle part looks like very much like this Atiyah bot Donaldson simplex.
Yeah, right. Okay.
But then you have the two Lie algebras, the one coming from the gauge group and the other one coming from a spin for the manifold.
Yeah.
And the part coming from the manifold is going to give you negative directions. I wonder if, of course, your variations depend on the rest of fields. So I wonder if I impose, I mean, from a math point of view, I cannot, but even if forgetting about that, if I impose that nabla is nabla minus, and I keep track of the dependence of nabla on the rest of fields, does this solve this problem of negative directions in the?
Yeah, I don't know, but I don't think so. I don't think so. Yeah, I don't see that working that way, but I don't know. The just slightly related point, the negative directions in this that I'm seeing here, different ones, but the negative directions I'm seeing here are associated to the fact as to whether you have, they might appear in a moduli space, but they're only going to appear in a moduli space if you have more than one supersymmetry. So if secretly you're preserving more killing spinners, then you would see these things as appear as extra negative directions in the moduli space. If you did the naive calculation, you'd then have done the wrong calculation because actually there was more supersymmetry, but that's, yeah. But I don't think that's connected with what you're saying.
Yeah, I'm actually kind of freezing the complex structure.
Yeah.
In my question, and yeah, I don't know. There should be some Keller moduli space there, right?
Yep.
It's curious that I don't know what it is, but
Yeah. No, absolutely.
If I can make another remark.
Yep.
Perhaps this is secondary, but from the point of view of four-dimensional theory, this Keller metric on the scalar manifold needs to be induced by a negative line bundle. So it needs to be the curvature of the Chern connection on a negative line bundle.
Mm-hmm.
Can you see this fact at this infinite dimensional stage?
Yeah.
Negative meaning what? What it means negative?
That the curvature of the Chern connection defines minus a positive definite Keller metric.
Oh.
So opposite to an ample, essentially, or positive line bundle.
Yeah, so you see the same, this metric on Z has the same property.
Oh, really?
Yeah.
So
actually, the metric on Z I'm writing is actually the metric on the line bundle, on the total space.
I see very well.
And what happens is that it's got a radial direction, but the radial direction has the other sign from the rest of one of the things is that that radial direction has a different sign, which from the rest of the space, which is just the statement you're saying, I think.
So by construction, it is that way. I see.
Yeah. Yep.
Ah, very well. Okay. I see. Thanks.
Mm.
And because I know Jeff likes flows, so what is if I take the normal square of the moment map and I take the gradient flow for that, do you know what this flow gives you?
Yeah. So let me write something else. So yeah, very good. So the potential, if I thought about this from a d = 4 point of view, the potential was given by some dw, okay, let me just dw star minus 3w squared plus the trace of the moment map squared, the norm squared of the moment map. So if we set involutivity, this is 0. So that the norm of the moment map should be none other than the potential, but this should be the generalized Ricci scalar, because it's just the restriction of the theory to the internal part of the space. So now, yeah, it's a slight caveat, but essentially it's going to be, it should be just some generalized Ricci flow. And in particular, the square of the moment map should be none other than the generalized Ricci scale.
When you say involutivity here, this is basically like assuming pluriclosed of the background.
Yeah, so this is, sorry, pluriclosed.
Yeah, okay. I just want to make sure.
Sorry. So again, if I use the fact from the four-dimensional theory, now there's something slightly subtle here, because I told you that the G-diffs, the Lie algebra was sort of isomorphic to sections of E. So to take the square of this moment map, I need some metric on the Lie algebra. Actually, I guess here it's okay. Sorry, I'm used to thinking about it in other problems. So yeah, you should be, well, you could do two different things to calculate this square of the moment map. You could use the generalized metric. And I think that's probably what you do. You would take the generalized metric. Or you could take the eta metric. But I'm pretty sure you would probably take the generalized metric. Yeah. So you have to define what you mean by the square of the moment map, but I think there's a natural one, which is you use the generalized metric, or the inverse of the generalized, what's the same, generalized metric.
Where this mu is given by the same formula from a few slides ago?
Yeah.
Can you maybe go back there quickly?
Sure.
Sorry. I see. Well, yeah, I guess, well, the second formula at least is written in the special case where you have this holomorphic volume form.
Yeah.
But maybe it's meant to just be the first formula in general?
Yeah, the second formula is what happens when you choose the pluriclosed, you satisfy the pluriclosed condition. I always have this holomorphic 3 form, but it's not necessarily completely closed. Now you can probably do, as I said, do this in the case where you want to drop the fact that you have the holomorphic 3 form, you just have a complex structure, but that's not the case I've explicitly looked at.
I see. Yeah. Huh.
But the low energy picture would tell you that this thing should be none other than the square of this should be none other than the Ricci. Now there's a slight caveat, which is that what about this W term? So involutivity is slightly weaker than extremizing extremizing the superpotentials. There's a slightly stronger condition. So I think about, yeah, so this is true actually if I actually want to take d omega as 0. I'm actually setting this, or probably it's not d omega, probably, sorry, I probably want to take, so this, if I take this condition, if I impose that condition, which is slightly stronger than just the involutivity pluriclosed thing, then this is true, I think.
The superpotential is this Gukov-Bachau-Witten, or?
Yeah, it's related to that, but it's slightly generalized because we haven't assumed any integrability yet. So it's actually, the superpotential is something like, let me tell you explicitly. Sorry. Well, it's roughly something like d omega plus I h wedge. And there's some powers of the dilaton. Probably there's an e to the minus 2 final. When you vary this holomorphically, you would vary, you'd vary this thing, and it would tell you that basically tells you that sort of the 1, 2 plus 0, 3 components of this thing have to vanish. Mm-hmm. And when you vary these guys, it tells you that this thing is closed.
Right, but already pluriclosed implies that W is 0. Oh yeah, but not DW. Yeah, DW wouldn't be.
Yeah, so this condition is a little stronger than the pluriclosed thing, I think.
Yeah.
But you may be able to do all this without reference to the holomorphic to the 3 form. I mean, I think you could probably do it all on this slightly weaker structure and still make sense of the moment map and so on. And the key thing is, like, I mean, the reason, well, you know this, right? The reason that you can't have any torsion in the solution is because of the Dylaton equation of motion. So, you know, there's equations of motion like Ricci plus h squared plus del phi is 0 or something, right? Or Ricci, maybe even just Ricci plus. So some Ricci mn. Ricci mn is 0, and then there's something that looks like I would write as d star. It's in minus 2 phi h is 0. And then there's a Dylaton equation which looks something like this. Involves the Ricci scalar and involves h squared. And it's setting this to 0, which gives you the no-go. If you drop that equation, then you can have solutions which violate the no-go theorems. So there's something yes, I think this picture where I've got the Dylaton is a little bit too strong. You kind of want to go back to the case where the Dylaton isn't really playing a role. If I understand.
Or at least that you just don't impose the final equation. Maybe.
You just don't impose the final equation, yeah. So the problem here is the final equation follows from the supersymmetry. So all these conditions I write down imply that this has to be true. So, but I think, yeah, just as you said, Jeff, I think the way to relax it somehow is to go to the weaker structure. That would be my guess.
Well, maybe we're finally done. Are there other questions? What do you want? Okay, sorry, please. Yeah.
Sorry. So this small GDIF, the Lie algebra.
Yep.
That one actually corresponds to, like, not really to the sections of E, but like sections of E modulo the symmetric part of the bracket.
Yeah, exactly.
Okay, I see. So okay, so it's basically the kind of the infinitesimal, all whatever vector fields on the total space of the Courant algebra.
Yeah.
Okay, and they integrate to like a global automorphism.
Yeah.
Okay.
The dual of that vector space is a bit better defined, because you can think of it as objects that are closed in some way.
Interesting. Thank you.
Okay, well, maybe, yeah, let's thank Daniel. That was very nice, very interesting.
Pleasure.